In this video, I'm going to be going over ways of post-processing heat flows in Thermal Desktop. The first question is, why do you want to study the heat flows? You can gain a better understanding of both the model and the system that is being modeled. How does the heat from a short duration, high power component make its way to the environment? You can verify the model is functioning as you intended. You can find and fix modeling problems. For example, you might find a contactor that should be 1.05 watts per K, not 105 watts per K. And you can find and fix system problems. The small portion of unblanketed aluminum facing the sun absorbs and conducts heat into the system faster than anticipated. Alright, so we're going to go over some terms. The first is imposed heat, represented as Q. This is the heat applied directly to nodes. A positive value is into the node. The sources for this would be heat loads that you define, heaters, and environmental heating. Then there's the heat rate, HR. This is the heat flow through a conductor between two nodes. It is positive from node A to node B as ordered by conductor definition. It can be linear or radiative. Then there's Q flow. This is calculated heat flow between groups of nodes, positive from group 1 to 2. So it's very important to distinguish between imposed heat, Q, which is applied to nodes, and the heat rate, HR, that flows through conductors. And now the save files. Most processing tools will use the save file, or the CSR if you're using that. Information about heat loads, conductors, and capacitance must be stored in the save file for it to be post-processed. By default, not all data is stored for a transient. It is for a steady state, but not a transient. On the Output tab of a case, click either All or Incident Heat, Capacitance, and Conductors. I did the case and go to the Output tab. I've selected All. This is what goes into the save file. This is what goes into the text.out file. So this is what you need for our post-processing tools. We're going to start with the model browser. When you're viewing a post-processing window, the model browser will provide more information than just those color contours. There are tools under the Options menu. The first and default is Current Post-Processed Results. It provides text for whatever is shown in the color contours. So if you're looking at temperatures, it shows you temperatures. If you're looking at heat loads, it shows you heat loads. Then there is Heat Map, showing post heat loads, Q, conduction in, HR, and conduction out, also HR, of the selection as a group. The conductors are identified as linear or radiative. Then there's Node Map, which is similar to Heat Map, but lists details for each node in the selection. Then there's Node Tabulation, summarize Q and heat rate for each node in the selection. Heat loads will show only Q for the selection. And then there's heat flow between submodels. This is a quick way to summarize heat flow between two submodels or one submodel and all others. So if I select a submodel, you can see this is showing temperatures for each node in the selection. I clicked on battery. That's because I'm currently showing temperature, Options, Current Post-Processed Data. Let's change that to Heat Map. So this shows that at this time step, total Q was 3 watts, 0.27 watts was conducted in, and 1.92 watts were conducted out. The type of conductor is either L or R, linear or radiative. And this does not show all of the conductors, just those with the highest heat rate. Then we have node map. This will only display for less than 200 nodes. So if we go back to a submodel, you can see it's similar information presented differently, but it's showing each node along the way. The Q, energy in, energy out. This is a good time to mention that for any of these, you can right-click and select Save to Text. You have some control over what is displayed under Options, Node Map Options. Most of this applies to FlowCAD, but there's also the heat flow cutoff criteria. Next we have node tabulation. The node, temperature, capacitance, imposed heat, CSG, net Q, and linear and radiation. Under heat loads, you'll only see the imposed heat Q. There's no conduction shown. Now let's look at options, heat flow between submodels. Select the From submodel. We can select Case. And we can select one particular submodel, or we can leave this global for all of them. So positive numbers are flowing into case, which means that 30.7 watts are being rejected by the case to space. And this is a summary of all the heat that's flowing between case and all other submodels. It does display case as well, as you can see that's really 0. Let's discuss the color contours. The first thing you can do is set node data to heat rates. This will show the imposed heat Q from all sources, and you can also set it as a flux. Or you can create a new type of data set, heat rates. If you set a heat rate data set, it will show the environmental heating rates only. This uses the orbital heating database, so not the save file or the CSR. Please note that if you have some logic that switches between different orbit heating rates, it won't be captured by this. You can also set heat flux between nodes. Show heat flux between two groups of nodes. You must define the two groups. One, but not both groups, may be set to all. And heat flow map between submodels. This is an interesting one. It changes the model to a wireframe and superimposes a heat flow network where each point represents a submodel. Now these last two are not compatible with EasyXY Plotter when you're looking at a transient. First, we can edit the current default data set. Instead of showing temperature for nodes, we can show the heat rate. And I can divide by area. Now this is showing all Q on each node. This includes environmental heating. If I want more information on that, I can set Options, Current Post-Process Data, select a submodel, and it will now show me the Q for each node instead of temperature. Now we can add a new type of data set. This will be heating rates. Now I need to select my orbital heating database. pick a time. I can select what I want to see as long as it was generated. This is an actual Keplerian orbit, so it wouldn't have any of the diffuse sky or sky AR. And if I want to make it a flux, and exactly what I want to see. Set current and close. So now this is only the environmental heating. We can also plot this. And you can see certainly where the shadow is, but it doesn't go to 0 because I'm including planet shine. I'll create another new one. Heat flux between nodes. Select the save file. And I'm going to guess there's a node case.22. You can see all the options we have here. Linear conductor, radiation, fluid ties, whether to make it a flux, how to define that heat into the node or out of the node. I only selected one node. You can select several nodes. Let's go ahead and edit that and just make it case. Now this shows all of the conductors, including case. All right, next let's take a look at heat flow map between submodels. I can select a time. Set current and close. So I see this is a little bit more abstract. This lets me see, for example, solar panels are sending a lot of energy to space. That's that red line. So it breaks up each submodel and gives you an indication of how much heat is flowing between them in a sort of schematic. I would have a couple results queries. QFlow from results creates one or multiple tasks that can take results from one or multiple save files. And then the heat flow between two groups will be written to an ASCII file. You can select XLS, text, or data file at each output interval. Groups can be defined by nodes, submodels, or domains. The save files do not need to be generated from the current drawing. Now, if you're using domains to define the groups, that information is taken from the current drawing. So these tasks can actually be imported from other drawings. Let's also analyze heaters from results. This is very similar to QFlow. This will create an ASCII file that summarizes heater operations in a save file. The columns that are output are defined in the Thermal Desktop User's Manual. These are under Thermal, Post-Processing, QFlow from results, and Analyze heaters from results. So the first thing I'm going to do is add a task, and you can give it a name. Add results. Select this save file. Now I have some options down here. By default, it will cover all times, but you can certainly say, no, I don't need all times. I only want after 400 seconds, so you could put in 400 or something like that. And here's where you define your groups. Add. Now we have these brackets and braces. You can look in the Thermal Desktop User's Manual to see the best way of doing these, that they can cover ranges or wildcards to some degree for node numbers. I'm just going to do a submodel, say case to avionics. And I'm going to click OK. Let's click the task and say calculate. It only created one pairing, so that's what these columns represent. If you have multiple pairings, they'll just continue with more columns. Expand these a little bit. So this column is the heat flow, total, linear, radiation, and if there are any fluid submodels. And we know that this was from case to avionics. This is the steady state that was at the start of the analysis, and then we immediately go into time 0 for the transient. So it shows an output at each output interval and lets you know what the Q is. This is a very simple use of it right here with just one submodel to another, but you can define as complex groups as you like. That's the end of this video on post-processing heat flows. Thanks for watching.